Hello, it's me Omra Sapkota. Today I am going to present about assignment of RFIC passive device theory and design. I'm going to present about chapter 4, that is example of design and fabrication of RF device using IPD technology. Here I'm going to show some contents. We have IPD design flow, schematic circuit design, circuit level simulation, 3D EM simulation, different kind of IPDs, and I mainly focus on these things: low pass filter, band pass filter, balloon, power divider, direction coupler, SOT packaging, and comparative analysis. Mainly in this book is primarily about practical design of IPDs. It would be ways to discuss some designs such as IPD design flow, schematic circuit design, circuit level simulation, 3D EM simulation, and different kind of IPDs like balloon, power divider, bandpass filter, low pass filter, and other result and layout. There are several approaches for designing IPDs, and the methods used to verify the performance of IPDs for their insertion loss or return loss and isolation at the desired center frequency, and the small outline transistor packaging method will be presented in this chapter. In this section, IPD design flow. What is IPD design? Thin film integrated passive device have developed to replace discrete passive component, that means IPD, and industry trend drives by microwave, high brightness LED, digital device, and mixed signal applications. Mainly there are 5 types of IPDs. In this chapter there are 5 different kind of IPDs. They are WLAN low pass filter, LTE band pass filter, WLAN balloon, LTE power divider, RFID direction, are mainly used as design and fabrication example based on the optimization manufacturing processes. We mainly discuss in this section about topology section, circuit diagram, circuit level simulation, 3D EM simulation. Those are in next slide. In order to perform and cost target a general design methodology, which is seen in figure 4.1, and the IPD design methodology. Here we can see modeling design. Here are some component which has been used in IPD design, and this is the layout after the simulation of the result, and we have to lay out the structure. This one is a marks array and fabrication section. In this section those components are fabricated, and after that the results are measured by using IPD chip and analyze the result. This one is the design low pass filter. This one is the schematic diagram of low pass filter, and this is the simulated result. What is the main purpose of the low pass filter? We can say that for passing unwanted signal and to eliminate or attenuate harmonics, and in the such way the filter design starts from the synthesis of a standard third order Butterworth low pass filter using lump element. The layout was generated using 173 cadence bar to produce a chip size of 0.66 cross 0.4 millimeter square, which is seen here. The layout of the design low pass filter with the chip size this much. For more accurate design, low pass filter was simulated using ADS software, so which is seen in this figure. After completing the layout, the circuit was fabricated using gallium arsenide IPD process. This section we can see that some major insertion loss and return loss for the fabricated WLAN low pass filter. The fabricated low pass filter is shown in the right, low right, this section. By using this optimization method, we achieve a response closer to the specification. ADS software, the simulation by using ADS software is far better than this previous one, that is 147 guidance bar to show. And now let me introduce about bandpass filter. That is, what is the main thing about bandpass filter? The bandpass filter can bend the signals or RF front into of the both receiver and transmitter circuit to reject those noise that may interfere the sensing transmission, therefore that may damage for the bandpass filter in high desire. One of the method used for the transmission line structure to realize the filter designs are and next one is lumped LC type structure. Those has been calculated using these formulas, that is inductance, resistance, capacitance, and this Q factor, which we can using these those parameter which is mentioned in here. This is the configuration of bandpass filter construction by a differential transformer. This is the circuit diagram of the bandpass filter. Here two parallel resonators means these two resonators magnetically coupled with the transformer, this section, and each resonator has one coil inductor that we can see here, this L1 and L2, and an MIM capacitor which we can see here. These are the simulated result, simulated electric field distribution for the bandpass filter at different frequencies. This simulated result in 0.4 gigahertz, and this is in 0.9 gigahertz, and this for 1.4 gigahertz frequency. In this figure, we are going to describe about fractional bandwidth and the electrode size of the capacitor, and through which we can calculate it using this formula. Figure illustrate a simulated variation of the normalized transmission zeros and the fractional bandwidth when the electrode size of the capacitor WC are changing. When the WC is changed and the change in FVW and normalized transistor zero, that means NTZs, in which range it has been changed, we can say. In this equation, we use F1 and FH indicates the 3 dB bandpass H frequency. FR is the resonance frequency, and FZ is the frequency of the transmission zero. In this section, we are going to show about FIB. This figure shows that FIB image of the fabricated IPD bandpass filter and photograph of the final device of the measurement in top view. This one is top view, and this figure B is enlarged view of this bridge, and then figure C is cross section view of the air bridge. And in the same way, the figure C is bandpass filter attached to the subboard PCB with SMA connector, which we can see here. And in the E section, we can see the enlarged bar chip with a wire bonding connection. Here in this graph, we can see that the fabricated device shows that the different type of transformer has a coupled coefficient of 0.65 in this around 0.658 900 megahertz. And here we can see the frequency range, and this is coupling coefficient. Here is around 0.65 in 900 megahertz. Quality factor of a single inductor is 17.3 as shown in the figure. This around in this position we can see this around 17 point something. The two transistor in this section, this one is the simulated and measure result of the presented bandpass filter using the IPD process. Now I'm going to discuss something about Balun. Balun provides balanced output from an unbalanced input. Balanced output means what? The balanced output signals are defined as two output signals that have half of the input signal amplitude and are 180 out of phase. Means the output results is half of this input, and these are 180 degree out of phase shift with respect to this input signal. And this captures the insertion loss and return loss of the design WLAN balloon. A compact 2.4 gigahertz WLAN balloon designed and fabricated with a phase imbalance of less than 3 dB and very low insertion loss and return loss is presented here. You can see, and in this section we can see the simulation result are shown in this section. But in this section, the phase performance of the design WLAN balloon has been presented. This one is the layout of the design of the balloon, which chip size is 0.8 into 10 into 0.7 mm square, and the layout was generated using Cache and Bartuso to produce this dimension balloon. And this one is the overall simulated structure of the WLAN balloon by using ADS software, and these are the results. The insertion loss and the return loss were below 0.25 dB and minus, which we can see here in this section, these two section, and here also. And respectively, the phase imbalance was less than 3 degree and its amplitude imbalance was less than 0.5 dB. Yeah. And now I'm going to discuss about power divider. Conventional Wilkinson power divider are widely using RF front-end communication system for equal unequal power split within phase response at different output. Means the some power has been given from port 1 and the some output has been emitted from or output from port 2 and port 3 that might be equal or unequal, and we can find this capacitance inductance using this formula. The impedance of the lumped equivalent equals to the distribution transmission lines, and this one is the schematic structure of the distributed Wilkinson power divider. This is the 3D view of the proposed Wilkinson power divider model by ADS, and this one is the quality factor of the design inductor, which we can see here. And to generate this structure, we have some design procedure. The first metal line is covered by the second metal line, and two different type of capacitor are utilized to realize the MIM capacitor. This is the FIB image of the IPD power divider, and figure A is the top view, and B1 is the enlarged view, and C is the cross section of the enlarged ear bridge part, means this section of the power divider. Here is the relation between S parameter and frequencies measure of the fabricated IPD power divider in Korean University RFIC lab. Now I want to discuss about directional coupler. Directional coupler means which can direct the direction of the signal. Direction coupler are most frequently constructed from two coupled transmission lines set close enough together such that energy passing through one is coupled to the other. An essential feature of the direction coupler is that only couple power flowing in one direction, and this one the schematic diagram of the direction coupler, and this is the simplified layout of the directional coupler. Here C1 and C2 are implemented in the backend area of the interwing inductor to save area as well as to avoid using off-chip capacitors. Coupling coefficient and quality factor and inductance has been plotted here. According to this plot, way to define, there are number of interwind are used to reduce the areas and increase the mutual inductive coupling. As the trace winding is increased, both the inductance value and the coupling coefficient means here inductance and this coupling coefficient are increased, while the isolated the quality factor, this quality factor can be reduced in this way. You can see figure 4.27 shows a micro photograph of the direction coupler implementation in the IPD process with a chip area of 0.72 cross 0.72 cross 0.82. A good implementation of two metal lines in one space between the primary side and secondary side is achieved, and could meet our requirement as shown in the figure 4.27 B and C. B1 is a cross section of the direction coupler, and C is the enlarged form of the of the ear bridge part of the direction coupler. Here figure 4.28 shows the simulated and measure S parameter of the circuit along with a comparison of the simulation and the measure it. Here simulated is this one and measure is this one. In every case S parameter are plotted here. In A, S21 the insertion loss, and S31 the coupling, and S41 the isolations are plotted here. IPD, the packaging provides a means of the protecting the chip from the environment and the handling damage, provide physical support for the chip, heat dissipation, interconnection for the signals in and out of the chip, and for attaching it to the high assembly level. This one is the obligation view or full view, and this one is the side view, and this section C is the top view, and D is the front view. So through this we can visualize the structure. The SOT packaging are the chip surface mold plastic molding type with lids on their two long sides into achieve a low cost and low profile. In this work we use SOT packaging for the fabricated IPDs, which are small in size and allow a higher border density, leading to a higher electric speed speed for system application. The SOT packaging is from different views are there these here. The internal structure of the WLAN, LPF, LT power divider, direction coupler, power divider, in WLAN balloon and example top view using SOT packaging are shown in here. Here we can see in this section. A is Lowpass filter, B is LT power divider, C is DES power divider, and D is balloon, and one example top view. And here is the some comparison. In general, a 6-inch gallium arsenide wafer was used for the fabrication. Generally, gallium arsenide device can be operated at higher power level than a silicon or glass device because it has higher breakdown voltage, more than 506-inch gallium 50 more than 50 6-inch gallium arsenide wafer and more than 3000 and WLAN balloon chips has been proceed with a base DC around 90% around 90% with proper DC specification control. Good DC chips can be achieved with the RF yield over 95%. This shows the improvement in the yield achieved by the work by comparison previous method to the outline processes. And here is the reference which I use. Is the book of published in 2015 by Professor Namyoon Kim and C. Wang and Y. Lee, and the book name is Practical Integrated Passive Device Technology. And this is the review of the IPD technology. And thank you for watching my video.